Very good afternoon and welcome one and all present here on the fourth session of day 2 of ATAL sponsored online 1 week offline FDP on unlocking the future, exploring the transformative power of 5G and beyond from 4th to 9th December 2023, organized by Electronics Engineering Department, Rajki Engineering College, Sonbhadra. It gives me immense pleasure to introduce and welcome our eminent speaker, Dr. Anand Sharma from MNIT Allahabad. Now, I would like to request Dr. D.K. Tripathi, DSW, and Associate Professor, kindly welcome with a plant. Please give him a round applause for him. Anand sir, please. Anand sir.
अच्छा
Dr. Sharma obtained B.Tech from Uttar Pradesh Technical University, Master degree from JP Institute of Engineering and Technology from Guna, and PhD in RF and Microwave from IIT Dhanbad. After that, he joined Government Engineering College Sonbhadra as an assistant professor and left the college in July 2019. Currently, he holds the position of assistant professor at grade 1 in Department of Electronics and Communication Engineering at MNIT Allahabad, Prayagraj. He has published more than 60 articles in the international journal and conferences of repute. He also presented more than 40 articles in national and international conferences. His research area includes MIMO antenna for IoT applications, circularly polarized DRAs, ultra-wideband and super-wideband antennas, wearable antennas, antenna optimization using machine learning. Dr. Sharma is working as an expert reviewer for international journal of repute such as IEEE Transaction on Antenna and Wave Propagation, IEEE Antenna and Wireless Propagation Letter, AEU and Optical Technology Letter, and so on. He is also doing some research projects on antenna funded by SCRB New Delhi, CST UP, MHRD New Delhi. His name is also included in the list of world ranking of top 2% scientists in 2021 database created by Stanford University, USA. Sir, we are very glad to have you here. Thank you so much for accepting our invitation. Sir, you are requested to kindly start your session and enlighten us with your kind words. Thank you, sir. Over to you.
thank you so much. So thank you so much. First of all, I am highly thankful because I have started my job as an assistant professor from here, from Rajki Engineering College Sonbhad, in 2017. Now again I come here to deliver a lecture on the recent trends in antenna design for 5G and beyond. So thank you so much to Dr. P.K. Verma and Dr. Himanshu Katihar and the entire department for inviting me here. So as the theme of this ATAL FDP is the 5G, the techniques related to 5G and beyond. So and my specialization is basically the antenna design, and in antenna design I am basically my specialization is dielectric resonator antenna. So I am focused on that. starting with I start this presentation with some basics of dielectric resonator antennas, and why and then I will move towards the basically towards the uses of that ceramic antennas in 5G technology and beyond, because as all of you know this thing that uh, as the technology is or generation is moving towards 5G and beyond, so basically we are increasing the frequency of operation. Okay, so so we have to design the antenna that is more effective for that frequency range. So let us suppose that we are doing in a millimeter wave frequency range or a terahertz frequency range. So ceramic antennas are more effective as compared to the microstrip antennas. So I deal with this dielectric resonator antenna in this presentation. क्या हो चेंज क्यों नहीं हैंग हो गया क्या? अच्छा अच्छा हाँ हो रहा है. So starting with a very basic, I think all of you are aware with this thing that what is an antenna. I actually discussed this this slide here because of one reason. Actually, here if you see in 1965, a Webster dictionary defines the antenna as a metallic device for radiating or receiving the radio waves. Okay, in after that in 1983, IEEE actually modifies this definition and says that it is a means for radiating or receiving the radio waves. Okay, so I think both the definitions are having the same basics, but the thing is in 1983 the term metallic device removed from this definition, which is given by the Webster dictionary, and the reason is that in 1983 American scientist Professor L.C. Sand discovered that the ceramic materials are also capable of radiating or receiving the radio waves. So IEEE actually he experimentally proves this thing that the ceramics or dielectrics are also capable of radiating or receiving the radio waves. So IEEE modifies this definition and removes the word metallic from the definition, okay, in 1983. So this is the this is some history of dielectric resonator. Actually dielectric resonators are basically used in designing of filters or in designing of oscillators. Okay, because as you know, as the name suggests, it is a resonator, so it is basically used to store the energy, to store the EM energy. Basically we are using the metallic cavities for that purpose, for storing the EM energy, but these dielectric resonators also facilitate these things. These ceramics, if you increase the permittivity of the ceramic, then more and more electric energy is E field is confined inside the ceramic. So it is a effective resonators. When you design the when you design a resonator with the help of ceramic, then it is more effective. So in 1939 it is discovered by Richmeyer. He is also a US based scientist, and after that in 1960 some application of dielectric resonators comes into the picture. In 1983 actually in dielectric resonators there are two different types of mode which is basically presents. One is known as a confined mode, another one is known as a non-confined modes. So if the modes is non-confined, then that type of modes having some radiation losses. So when you design a microwave filters or oscillators with the help of dielectric resonator, then you have to use some metallic cavity over that resonators to reduce these losses, to reduce the radiation losses. Okay. Professor L.C. Sen or Professor S.A. Long has developed or has actually used this phenomena of radiation losses, which is occurred due to the non-confined modes, and they remove the metallic cavity from the ceramic material, um, and uses a low dielectric constant. So as we reduce the dielectric constant or ceramic permittivity of the material, then more and more radiation losses are occur, and you will get a good radiation. So in 1983 these three scientists experimentally proved this thing, that ceramics are also capable of doing the radiation. Okay. Now now it is very popular in antenna engineers. Right now dielectric resonators are very much popular because it having a very low metallic, there is no metal present in dielectric resonators, so the metallic losses are fully absent. Okay. So as you increase the frequency, the skin in metallic radiator skin effects are more dominant, while in case of, because there is no metal present, so there is no skin effect type of phenomena, and you will get a good gain with the help of dielectric resonators. Okay. This is how the dielectric resonators are radiated, how the radiation occurs. So I already discussed this thing. These are the some of the advantage of dielectric resonator antennas. Like in dielectric resonator antennas, as I already told you, that it having a good gain, good radiation efficiency as compared to the metallic antennas or microstrip antenna, you can say that. It also avoid the surface wave, okay, surface wave phenomena in which is widely occurs in microstrip antennas. There is no such type of phenomena here, so you got a good gain value. Again, you can easily control the size and bandwidth of that antenna by changing the permittivity of the material. As the permittivity reduces, you will get a good gain because the quality factor becomes reduces. Okay. The another advantage, it is also available in different shapes, like we have a cylindrical shape, we have a rectangular shape, each shape having a different advantage. Like if you are using the cylindrical shape, then it can support, you can say that it can support the different modal patterns, like we have a T mode, TM mode and hybrid mode. Okay. So and each mode having its own radiation characteristic, so you will get different types of radiation property with the help of different shapes. Okay. Another and very important advantage of ceramic antennas are it having a very high dielectric strength. So you can use such type of antennas when we want to transmit a very high power, like in radar. Okay. It can withstands with a very large amount of power, that is more than 1 megawatt. Okay. This is some basic shapes which are widely used in DRA. Like we have a cylindrical shape, as I already told that because of this axis symmetry, it can support 3 different modal patterns like T, TM and hybrid modes. Okay. And each mode having its own radiation characteristic. So it having a good you can say that you can get a diversified radiation pattern with the help of cylindrical ceramic material. Similarly, we have a rectangular DRAs. It also having advantage of, because it having a 2 degree of freedom, so you can easily control its quality factor in case of a rectangular DRA. Okay, this is somehow you can this is some of the research area which is focused in case of a dielectric resonator. However, we are later on we will discuss some of the DRA application in 5G, specifically for 5G communication system. Like initially I discussed some basic thing, how can we generate the multi-band characteristic, or how can we generate the circularly polarization characteristics in DRA, how we generate the wide band, ultra wide band characteristics in DRA. So there are different techniques available to create a multi-band characteristics in DRA. Like you can use the multiple ceramics. Okay, each ceramic having you can say that having the different dimensions, and because of the different dimensions, each DRA are radiated in different frequency bands. Okay, similarly you can also use the another technique which is known as hybrid DRAs. Okay, in hybrid DRA this is the combination of, you can say that the ceramic as well as some other resonating structures like slot antenna or a microstrip antenna, and each radiator having its own resonant peak. By doing so you can generate a multi-band characteristic. Another feature is the generation of, you can say that, the multiple modal patterns inside the ceramic material, each modal pattern having its resonant frequency, or because of multiple resonating modes are created inside the ceramic. So each mode is corresponding, or each resonant peak is corresponding to a different modes. Okay, now I have given one of the example of my published paper, and it is based on a hybrid DRA. Hybrid DRA means it is the combination of some resonating structure along with the ceramic material. Okay, so here we are using a metallic patch which is also used to feed this ceramic. This is a alumina ceramic. Okay, when you feed this ceramic with the help of this patch, okay, so this patch having its own resonant peak which is at 2.5 gigahertz, and when you excite this alumina ceramic with the help of this patch, then three different mode patterns are created, or three resonant peaks are created. One is at 3.5 gigahertz, another one is at 5.1 and 6.1 gigahertz. So by doing so you can generate a multi-band characteristics inside a antenna. But there is a problem with this DRA, dielectric resonator antenna, that in case of DRA we have certain modes that is not used for radiation purpose, because it having a high quality factor. If any structure having a high quality factor, that means more and more energy is confined inside the structure, it is not radiating. Okay, that means this is the problem of DRA, that you have to find out which mode is a radiating mode and which mode is a non-radiating mode. Okay, so here if you find the field distribution, because if you see here in S11 characteristic we have a three different resonant peak, one is at 3.5, another one is at 5.1 and 6.1 gigahertz. When we see this the field distribution, then I found that all three resonant peaks are due to the hybrid mode characteristics. Okay, that means it having hybrid mode means both I think all of you are aware with this thing, that TE mode and TM modes, okay, where the EZ component, case of T transverse electric, the EZ component is 0 along the direction of propagation, while in case of TM HZ is 0, while in case of HE, that is hybrid mode, both EZ and HZ component is present, while one of the component is more dominating. That means either EZ is dominating or HZ is dominating. Okay, so in case of HE mode, EZ is more dominating. Okay, so when we plot the E field at 3.5, 5.1 and 6 gigahertz, then I found that three different hybrid modes are created. One is HEM11 delta, second one is HEM12 delta, and third one is HEM21 delta. And when we found its quality factor of different of these modes, then I found that it's the quality factor of HEM21 delta is approximately you can say that 30 times greater than HEM11 delta. So we found that this mode is a non-radiating mode, it is not a radiating mode. So actually the non-radiating modes also, there is a drawback of non-radiating modes, that it also affect the radiation characteristics of other modes like HEM11 delta and 12 delta. So you have to suppress that mode. Okay, so we have to we want to suppress this mode. So in this paper we actually use two different annular shape. If you see this thing, we are using two different annular shape on an opposite side. When I do this thing, then this type of radiation characteristics, or this type of E fields are generated, which is 180 degree out of phase, and these two field characteristic will terminate each other. And if you see this S11 plot, then the peak, resonant peak at 6.1 gigahertz is totally removed from the this spectrum. Okay, so we got only three resonant peaks. One is at 2.5 gigahertz, which is due to the annular ring. Another one is HE11 delta, and third one is HEM12 delta. Okay, non-radiating modes is removed from the spectrum. So if you are designing the dielectric resonator antenna, then you have to take care about these you can say that non-radiating modes. You have to find out which one mode is non-radiating, and you have to suppress it also. Okay, now there is another method of creating the multi-mode characteristics, that is with the help of you can say that with the help of multiple mode generation inside the array. So in these two papers I have developed the multiple modal patterns with the help of feeding structure. So there is a lot of explanation is there. We are generating three different modes like HEM11 delta, 12 delta, and TM01 delta, and each mode having its own resonant peak, and due to these three peaks it behaves like a multi-band antenna. Okay, another important characteristics which we have focused in current literature, and that is circular polarization characteristics. Okay, why circular polarization? I think all of you are aware with this polarization, the orientation of electric field. So we have generally two different type of polarization, which is a special case of elliptical polarization, that is linear and circular. Okay, in case of a circular, there is a condition that Ex, there are two orthogonal field component, one is Ex, another one is Ey, both are equal in amplitude, and there is a phase difference of 90 degree. Okay, by doing, if you are creating the circular polarization in any of the antenna, then it will create a characteristic that is the transmitter and receiver becomes, or you can say that receiver becomes orientation independent. दैट मीन्स आप किसी भी ओरिएंटेशन में रखेंगे एंड रिसीवर को, तब भी वो क्या करेगा, रिसीव. अगर लेट अस सपोज दैट इफ वी हैव अ लीनियर एंटीना, linear antenna always receive the maximum power when the polarization of transmitter antenna and receiver antennas are matched. That means अगर आपका ट्रांसमीटर एंटीना वर्टिकली पोलराइज है तो आपका रिसीवर एंटीना भी क्या होना चाहिए, वर्टिकली पोलराइज. अगर वो हॉरिजॉन्टली पोलराइज है और ये वर्टिकली है तो ये इसके लिए क्या करेगा, क्रॉस पोल का काम करेगा. दैट मीन्स मिनिमम पावर रिसीव होगी. व्हाइल इन केस ऑफ अ सर्कुलर पोलराइजेशन दिस इज नॉट अ केस. Let us suppose that if my antenna is horizontally polarized and my receiver antenna is circularly polarized, then it receives the power in any direction, from any direction. Okay, this is the advantage of circularly polarized antennas, and right now it is widely used because it is widely used in satellite communication actually, because when we transmit the signal from ground station to the satellite, then there are lots of atmospheric layers there, and there is a high probability of changing the polarization characteristic of the wave, EM wave, which is transmitted through the ground station. So such type of receivers are widely used in satellite communication circularly. However, we are also using in our towers also okay, circularly polarized antennas. While there is a drawback of circular polarized antenna, there is a lot of power wastage. Okay, power wastage is large in case of a circularly polarized antenna. Okay, how can you design? So as I already told you that if you want to design a circularly polarized antenna, then you have to actually satisfy two different conditions. One is two orthogonal component is equal in magnitude, that is Ex and Ey, which is equal in magnitude, and another condition is there is a phase difference of 90 degree between these two field components. So in this structure the author have used two different, if you see the strip lines, two different strip lines having the dimension is different, the length is different of these two conformal strip, while the distance between these two is lambda by 4. So as we see these as we put it into the 90 degree, then it will create the two orthogonal field component, that is Ex and Ey, while as you change the dimension of this strip, then it will create a path delay between the Ex and Ey component. This is a basic phenomena, that if you create a path delay between the two field line, then it will create a phase difference. Okay, phase difference is 2 pi by lambda into path difference. Okay, so as you create a path difference, some phase difference is created between two orthogonal field component Ex and Ey, and it will create a circular polarization characteristic. Same concept is used in this structure, in this antenna structure. It is also used for by creating the Ex and Ey component equal in magnitude and having a 90 degree phase shift. Okay, how we will create a wideband characteristics or ultra wideband characteristics? Okay, so we have a different types of, you can say that technique, like by in general you can say that wideband characteristics you can generate it by reducing the quality factor, or by creating the multiple mode patterns, or by combining the multiple mode patterns, as well as by splitting or sectoring the basic structure. It is also used to reduce the quality factor. Okay, so this is one of the structure which we have published in IEEE magazine, and it supports the ultra wideband characteristics having a frequency range from 3.1 to 10.6 gigahertz. The main, actually the theme, or you can say that the unique point of points of this structure is that it creates a ultra wideband characteristic by combining the three different techniques. First technique is hybrid antenna technique, another one is by reducing the Q factor, and third one is by combining the multiple mode patterns. Okay. So I will not go into the detail of this structure. You can say that is this antenna design. Okay, so more and less it is actually the combination of different techniques, that is so it is the combination of three different techniques. One is a hybrid antenna technique, multiple mode generation, and the quality factor reduction. Okay. Now I will move towards the theme of this FDP, and this is a some techniques, communication techniques, or for 5G and beyond. Okay. So DRA is right now these dielectric resonator antennas are widely used in 5G communication. Okay, as already you know this thing that antenna is a backbone for wireless communication. So firstly you have to design an effective antenna for transmitter for transmitting the EM wave and reception of the EM waves. Okay. So if you see what is the basic requirement of 5G communication, what is the basic requirement? High data rate, low latency. Okay. For that purpose you can design a MIMO. Okay, because in MIMO we have a multiple antennas on transmitter side, multiple antennas on receiver side. So it will enhance the capacity by improving the signal to noise ratio. Okay, there is a reliable communication link. Okay, another is in 5G we are also moving towards the higher frequency range, that is the frequency range is moving towards the millimeter wave. Okay, where we are talking about the frequency more than 40 gigahertz, and when you design a metallic antenna that having a frequency more than 40 gigahertz, then in that case the losses are very high and the antenna gain is very less in that condition. Okay. So while in case of a dielectric resonator antennas there is no such cases, there is no metallic part present in that antenna, so the metallic losses are less and you got a good gain when you design a dielectric resonator antenna at millimeter wave frequency range. Okay. Another important area is quasi isotropic antenna design. I think all of you are aware with the isotropic antennas. It is a hypothetical antenna which radiates equally in all the direction. It is not, you cannot design such type of antenna, it is a hypothetical. Okay. So but right now some of the researchers have developed a technique, and that is known as a isotropic radiation pattern. Isotropic, it is not completely isotropic, because in isotropic antenna it is radiated equally in all the direction in the 3D space, while in case of a quasi isotropic means it is omnidirectional in both the principal plane, that is E plane and H plane. Okay. So some of the researchers have developed this quasi isotropic radiation characteristics, and we are also focused towards the development of filtering antennas. Okay. If you are aware with the front end of the communication system, after antenna we have a band pass filter, okay, for rejection of out of the band frequencies or out of the band signals. Right now antenna researchers are develop some of the antenna design which is itself working as a band pass filter. Okay. It is also used for radiation purpose as well as for it is also used as a band pass filter. There is no need to accommodate a band pass filter after the antenna. Okay, antenna itself behaves like a band pass filter. So we will discuss how we design this type of antennas, quasi isotropic antenna with filtering response. Another important, very important right now, if you are doing some research or some project on antenna, then this area is quite, you can say that, quite useful, that antenna design for cognitive radio. Okay, this is right now, it is very famous. The researchers who want to design an antenna for 5G communication system, it is a more smarter antennas which is used for cognitive radio systems. Okay, beam splitting or beam tilting is the another phenomena which is used in 5G communication. Okay, beam splitting or beam tilting. So how can you design? Starting with a very basic thing, that is MIMO, multi input multi output technology. What is that? Multi input multi output. So in that case, we are using multiple antennas on transmitter side and multiple antennas on receiver side. So there are two different, you can say that, formats for MIMO antenna. One is a spatial diversity, another one is a spatial multiplexing. If you see carefully, in spatial diversity we transmit the same data from the different antennas, and it will enhance the reliability of the link. Okay. Similarly, in case of a spatial multiplexing, we actually divide our original message stream into the small section, and each small section is transmitted by the different antenna. Okay, and it will received by the receiver. So it will enhance the capacity of the system. Okay, so these are the two different format which is widely used to enhance the data rate. Okay, which is the very important, you can say that, very important for 5G communication system. Okay, now how can what type of research is right now focused on MIMO antennas? So we are focused on multiband characteristics generation in MIMO antenna, so that the same DRA, same MIMO antenna can be used for different frequency band applications. Okay, wideband characteristic generation has also been focused. And third and very important one is the isolation enhancement between the different ports. So in case of a MIMO, we are basically focused on two different types of isolations. Okay, one is related to the S parameter, another one is related to the far field. Okay, so this is one of my published paper on 2-port. This is a 2-port MIMO, and it supports the multiband characteristics. Now, as I told you in this slide, that we are focused on isolation enhancement, and isolation is when we are talking about the isolation, then in case of a MIMO, we are basically focused on two different types of isolation, and one is known as S, which is based on S parameter, another one is based on far field. So here we are focused on S parameter based isolation. If you see, I have used 3 different ground planes. Okay, initially there is a conventional ground plane, I have not doing any modification in that. So if you see the current and I excite only one port here, second port is terminated by the match load. Okay, when I excite the first port, then the current is you can see that it is uniformly distributed on the edges of the ground plane. Okay, after that I put this reflector on a ground plane, then you see that most of the current is focused on this side, which is excited, which port is excited. And when I place this metallic strips or these slitted ground plane, then most of the current is focused on this side, on the excited side. Okay, and if you see the isolation characteristic, that is mutual coupling between the two ports, then for the conventional ground plane it is approximately 10 dB, okay, or less than 10 dB. After that, when I put the metallic strips on the, or reflector you can say that, on a ground plane, then it dips down towards the 20 dB. And when I use this slitted ground plane, then it again dip down and goes less than minus 30 dB. So this is the, you can say that this is a isolation enhancement using S parameter. Okay, there is no discussion on a far field right now, but far field is very important. Okay, this is the another case of isolation enhancement using S parameter, or using S parameter. Here we are using two different apertures and it is of a mirror image. ये आप देख रहे होंगे, ये इस डायरेक्शन में टिल्टेड है अपर्चर और ये इस डायरेक्शन में टिल्टेड है, दोनों अपोजिट डायरेक्शन में टिल्टेड है. तो as you tilt in opposite direction, so different types of polarization are produced by the different ports. That is, if it supports the left handed circularly polarized, then this port supports the right handed circular polarization. So this is known as a polarization diversity. Okay, if you are using polarization diversity, again you will get a good isolation which is S parameter, based on S parameter. Okay, now I will come to the point of far field isolation, why it is more important. If you are talking about an antenna, then far field are more important as compared to the S parameter. ठीक है, S पैरामीटर ठीक है, S पैरामीटर हम लोग देखते हैं कि कितनी पावर हमने इनपुट में दी और कितनी पावर ट्रांसमिट हो गई, कितनी रिफ्लेक्ट बैक. दिस इज द S पैरामीटर ना. if you I am talking about S11 reflection coefficient, ठीक है, what is reflection coefficient? Reflection coefficient is simply signifies that what you have applied to the port and what is returned back to the same port. Okay, ये तो ठीक है, but we have to focus on a far field. ठीक है, जब हम far field को isolated करेंगे, then it will coverage a more area in a spatial domain. Okay, तो यहाँ पर we are actually focus on two different parameters in case of a MIMO antenna, and one is known as envelope correlation coefficient and second one is a diversity gain. Envelope correlation coefficient actually tells us how much both the ports are correlated to each other. तो इसकी वैल्यू क्या, ECC की वैल्यू क्या होनी चाहिए किसी भी efficient MIMO एंटीना के लिए, क्या होनी चाहिए, कम से कम होनी चाहिए, because both or the ports are uncorrelated with each other. Okay, तो now there you can measure the value of ECC by two ways. One way is which is based on S parameter, another way is by using the far field parameters. Okay, far field produced by the different ports. Okay, so as you already see the how can you reduce the ECC value with the help of S parameter. Now we will focus how we can generate or how we can reduce the value of ECC using far field. If you see this antenna, this is a 3D type of antenna. Here we are using the 4 different ceramics, alumina ceramic. One is if you see carefully, one is along Z direction, because it supports the HEM11 delta mode, and HEM, the radiation characteristic of HEM11 delta mode is towards broadside. Broadside means theta equals to 0, phi equals to 0. along this direction. Okay, if this is a radiator, then the radiation is along this direction. Okay, so I have placed this dr1 along z direction, dr3 along y plus y direction, dr2 along minus z direction, and dr4 is along minus y direction. Okay, by doing so, if you see the radiation characteristics of dr1, then dr1 is radiated maximum radiation. This red portion denotes the maximum radiation. The maximum radiation of dr1 is along plus z direction, the maximum radiation of dr2 is along minus z direction, dr3 is along plus y direction, and dr4 is along minus y direction. So each port having a different radiation characteristic in different direction. The maximum radiation is different. ठीक है, मैक्सिमम रेडिएशन क्या है, dr1 का प्लस z डायरेक्शन में, dr2 का माइनस z में है, dr3 प्लस y, dr4 माइनस y. So each radiation or each far field characteristic of each antenna is uncorrelated to each other. So that's why the value of ECC using far field is lesser for this structure. Okay. Now another technique to improve, or you can say that to reduce the value of ECC is with the help of frequency selective surfaces. Okay, FSS. FSS. We can also use FSS, frequency selective surfaces, okay, to tilt the radiation pattern. If you see,
This is smart reflecting surface you are talking about.
it is not a smart. Smart means
Smart means as per the channel condition.
no. That is known as reconfigurable intelligent surface (RIS), where we are using the diodes, okay, varactor diode or pin diodes, ठीक है, to tilt the radiation pattern dynamically. But it will provide you a static radiation pattern, a static tilting. It is not a dynamic tilting. Okay, so if you see this structure, so here we are using the unit cell, which is a triangular shaped unit cell, and it is the dimension is continuously increasing from this common. This is a common cell, number one, and then the dimension is continuously increasing along, and 2, 3, 4 is same on this side, 2, 3, 4 is same on this side. Okay, by doing so, it will create a different impedances, and this different impedance actually tilts our radiation, or you can say that in another way, you think this thing as there is a change in phase gradient. There is a continuous change in phase gradient. Okay, when you move from 1 to 2, then 3, and then 4. Okay, so initially when I not use the frequency selective surface, the radiation pattern is broad-sided. Okay, the red portion is along theta equals to 0, phi equals to 0. When I place the FSSS, frequency selective surface, that having the gradual increasing in the dimension of unit cell, then the pattern is tilted, and this pattern is tilted along this direction, along plus 45 degree, you can say that, and dr1, the radiation pattern obtained from dr1 is tilted to minus 45 degree with the help of this. So again, by using FSSS, okay, you can design a antenna or MIMO antenna that having a reduced ECC value. Okay, if you are using in the same structure, if you are using the diodes, okay, or active elements, then you can tilt it dynamically. You can create a tilting, dynamic tilting, and that is widely used right now. It is widely used in reconfigurable intelligent surfaces. Okay. Now actually I want to discuss something about the antenna design for cognitive radio, which is widely used right now in 5G communication or intelligent communication. Okay. So before starting this antenna designing for cognitive radio, I want to discuss something about the reconfigurable antennas. Okay, because in cognitive radio you have to design an antenna which is reconfigurable in nature. Okay, so how can you reconfigurable means dynamically you can change its frequency characteristics or polarization or radiation pattern. Okay, it is widely used in efficient use of spectrum, that is used in, you can say that, in cognitive radio. Okay. Mm. So different types of reconfigurable antennas are there, like we have a frequency reconfigurable, pattern reconfigurable, polarization reconfigurable, hybrid. Hybrid means this is the combination of frequency pattern, frequency polarization. That means frequency is changing dynamically. Okay, pattern means pattern is changing dynamically. Polarization is changing. Okay, with the help of pin diode or varactor diode you can change it. Okay, how can you create? So you can create the reconfigurability by electrically, optically, physically, or by using the material change. Okay, generally we are as an antenna engineer we are basically focused on this electrically reconfigurability, where we are using the pin diodes or varactor diodes, okay, to create a frequency reconfigurability. These are the frequency reconfigurable antennas. What is that? So if you see this structure, this is a dipole, simple dipole antenna. All of you have seen this type of structure in Balani's book initially. So here we are using the two switches, or authors are using the two switches, two silicon switches, because this is an optical antenna, so we are using the silicon switches. Okay, and if you see, when both the switch are closed, then in that case what is the length of this antenna? This one. Okay, and it is resonating at 2.16 gigahertz. Okay, when both the switches are open, in that case the antenna length becomes this one, and the resonant frequency comes at 3.15 gigahertz. दिस इज द फिनोमेना. ठीक है, जब एंटीना का साइज बड़ा है तो वो कहाँ रेजोनेट कर रहा है? 2.16 गीगाहर्ट्ज. जब हमने क्लोज कर दिया तो उसका छोटा हो गया साइज, और नाउ इट बिकम्स द रेजोनेंट पीक बिकम्स 3.15 गीगाहर्ट्ज. ओके, तो सिमिलरली we can also use the varactor diode. In case of a varactor diode, you can, if you change the reverse bias voltage of a varactor diode, then you can change the capacitance value. As the capacitance is changing, the resonance is changing, because the resonance, what is resonance? Resonance is simply, you can say that magnetic energy is converted into electrical energy is converted into a magnetic energy simultaneously, that is XL equals to XC. Okay, so now if you change the capacitance value, then the resonant peak is shifted on upper frequency side or a lower frequency side.
And from where is inductance resistance is there? Because from varactor diode we get the capacitor. Inductive effect and resistive.
It is also there. But actually it more effect on the capacitance. As you change the reverse bias characteristic of a varactor diode, then more and more change in on a capacitance value. Okay, that's why the frequency is shifted either on a left side or a right side. Okay, इंडक्टेंस का इसमें बहुत ज़्यादा फिनोमेना हम लोग चेक नहीं करते एक्चुअली. ठीक है, हाँ इंडक्टिव इफेक्ट तो आएगा ही. because it is made up of RLC components na. Antenna is actually, when you design, when you plot its circuit of any of the antenna, then it is simply a resonant circuit RLC. ठीक है, अब वो कैसे भी हो सकता है, it is it depends upon how you design, ठीक है, बट RLC इफेक्ट तो रहेगा. ठीक है, अब आप क्या कर रहे हैं, कैपेसिटर वैरेक्टर डायोड लगा के उसका कैपेसिटेंस चेंज करने की कोशिश कर रहे हैं, ताकि जो रेजोनेंट पीक है वो शिफ्ट हो सके. ठीक है, नाउ this is another example of this frequency reconfigurability, where we are using the varactor diode and a pin diode to shift the resonant peaks. Now come to this antenna designing for cognitive radio. Okay, so cognitive means actually we are also use SDR, software defined radio. This is more modified version of SDR. You can say that it is, here we have a here you can sense, first you sense the RF environment and characterize the propagation channel, and then starts the communication. Okay, so what I think all of you are aware with this CR fundamental, but I give some small scenario that in CR, in cognitive radio, we are basically talking about two different users. One is a primary user, another one is a secondary user. Okay, primary user own the spectrum, he has a license. Okay, and the secondary users are those who can utilize the spectrum when the primary users are not used that spectrum, that part of the spectrum. So the CR system having the capability that it identified where the spectrum is not utilized, and then assign that part of the spectrum to the secondary users. Okay, so we have to design an antenna that first sense the entire spectrum and find where the spectrum is not utilized. Okay, and then starts communication. So we have to design an antenna that having the wideband characteristics, as well as when you transmit the information, then it becomes a narrowband antenna with a reconfigurable characteristic. ठीक है, तभी तो पहले स्पेक्ट्रम को सेंस कर लेंगे, सेंस करने के बाद पता करेंगे कि वेयर द स्पेक्ट्रम इज नॉट यूटिलाइज्ड बाय द प्राइमरी यूजर. देन जब हमको पता चल जाएगा तो क्या करेंगे, तब कम्युनिकेशन स्टार्ट करेंगे. और वो कम्युनिकेशन हो सकता है कि कभी 2.4 गीगाहर्ट्ज खाली है, कभी 3.3 से 3.6 खाली है. तो वी हैव टू डिजाइन कम्युनिकेशन एंटीना इज रिकॉन्फ़िगरेबल इन नेचर. ठीक है, रिकॉन्फ़िगरेबल होना चाहिए. ओके, तो हाउ कैन वी डिजाइन दिस? There are two different scenario where we have a interweave and underlay. These are the two different modes. So in case of an interweave, I think all of you are aware with this interweave, where if the primary user use that is part of the spectrum, that is not used by the secondary user. Okay, the unutilized part is used by can be used by the secondary users. Okay, while in case of underlay, both primary user and secondary user use the spectrum simultaneously, while it is not, the communication of primary user is not affected. The primary user are not affected, the communication of primary user is not affected by the secondary user. Okay, so how can we design? This is some fundamental of CR. Now how can you design the antenna, such type of antenna? So here if you see, this is the first antenna which is developed in 2014 by White Tong, and he developed actually two different antennas developed. One is for interweave operation, another one is for underlay operation. Okay, इसके बारे में बहुत ज़्यादा डिस्कस नहीं करते हैं, हम लोग यहाँ पर आते हैं which is right now it is more important, the designing of multifunctional MIMO CR system. Okay, where initially जो conventional MIMO CR systems थे, where we have a where we have a one wideband antenna and the communication antenna which is for interweave and underlay is a MIMO antenna. Okay, while right now we are using the same MIMO antenna for sensing purpose as well as for interweave and for underlay, same antenna. How can we use it? This is one of the example. However, we have also published one paper on this topic with the help of DRA, and it is published in a transaction currently. This is published in 2019 by some other research group, and it is based on microstrip antenna. It is initially, this is a wideband antenna. This is a wideband antenna. Okay, and we have oh sorry, authors have created this antenna into a MIMO configuration, and it is working in between 2.5 to 5.5 gigahertz, which is somehow wideband. You can say that. So for sub 6 gigahertz. Okay. After that, after designing this wideband antenna, which is working from 2.5 to 5.5,
These are dielectric resonator.
no. This is a printed antenna, patch antenna. ठीक है, we have
Metallic part is there.
huh?
Metallic part.
Metallic part is used for a radiation purpose here. ठीक है, while we have also published recently, we have published one paper which is for cognitive radio, and it is dielectric resonator. Actually, there is some drawback of these printed antennas when we use for cognitive radio. We will discuss that thing later on. Right now, we are using this, or authors are using this CRR structure, CSRR, complementary splitting resonator. Okay, and here the authors have used the pin diodes, and here the author have used the varactor diode. Okay, and place this structure on a feeding part of the antenna, on this part. Okay, the reason is that initially, if you see when all the pin diodes are on, then it behaves like, then this structure behaves like a all pass filter. This structure behaves like a all pass filter, and when when S1, S2, S3, S4 is on, that means this one is S1, these are pin diodes, S1, S2, S3, S4 is on and S5 is off, then it behaves like a all pass filter. Okay, in the second scenario, when all the pin diodes are off, when all these pin diodes are off, then it behaves like a band pass filter. Okay, narrow band pass filter. This is a all pass filter, this is a band pass filter. And these are the two scenarios which is discussed here. There is one more scenario where it behaves like a notch filter. Okay, which is not given in this slide. Okay, so initially, if you see this structure, when this characteristics is achieved when S1, S2, S3, S4 is on, S5 is off. Okay, then this type of characteristic is achieved. What is that? This is a wideband characteristic, and it is used for sensing purpose. because this is a wideband antenna, and wideband antenna is basically used for sensing. Okay. Second scenario is this one, when S1, S2, S3, S4 is and S5 all pin diodes are off, then in that case it behaves like a band pass filter, and at the same time we are changing the reverse bias voltage of this varactor diode. As we change the reverse bias voltage, the resonant peak is shifted towards the higher frequency. Okay, and it is used, such type of antennas are used for communication purpose in case of a interweave operation. Interweave के केस में ही use होगा, because in case of a interweave, when the primary user use the spectrum, the secondary user not use. Okay, so this is for interweave. Now for underlay के केस में क्या हो सकता है, जब we are using primary user and secondary user use the spectrum simultaneously. Okay, but if the secondary user affect the communication of primary user, then you have to remove that secondary user. तो यहाँ पर हमको किस तरह का एंटीना डिजाइन करना है, which is having a band notch, reconfigurable band notch. Reconfigurable band notch के लिए हमने क्या किया, again we have described another type of structure where S1, S2, S3 and S4 are on while S5 is off. In that condition it behaves like a band notch, it having a band notch characteristic, and after that we change the reverse bias characteristic of varactor diode, and this band notch become reconfigurable. Okay, at that time this spectrum is used for an underlay operation. So we have found three different characteristics. One is sensing, another one is for interweave, and third one is for underlay. Okay, this is entire characteristics for in case of a printed antenna or metallic antenna, when we are using, because printed antenna having a low gain, and if you are using the diodes or active elements over that, then again the losses become more severe. So the actually the gain of such type of structures are very less. Okay, that's why we have we are using a dielectric resonator, because dielectric resonator having the inherent characteristic that it having a large gain as compared to the patch antennas. Okay.
So in case of dielectric resonator, how that antenna capture the signal, because no metallic part is there?
So I have already discussed this thing initially, that actually when you excite that ceramic material, then some standing waves are created. Okay, some standing, but because the dielectric boundary is not perfect boundary, we have two different types of mode patterns, like we have a confined mode, we have a non-confined mode, because there are some losses. Let us suppose that if non-confined mode are created, then the wave strike on the boundary of the dielectric, and then some of the EM wave is transmitted and some is reflected. Okay, so initially when we are using the dielectric resonator for designing the filter and oscillator, then we are using the metallic cavities over it. Okay, after that actually if you reduce the dielectric constant of the material, then these confinement of the electric fields are lesser. ठीक है, जैसे जैसे कम करते जाएंगे वैसे वैसे कन्फाइनमेंट और लेस होता जाएगा. ठीक है, तो रेडिएशन लॉसेस और ज़्यादा होते जाएंगे. ठीक है, तो इन दैट केस when we are using the dielectric resonator as an antenna, then you have to remove that metallic cavity, okay, and reduce the permittivity of the material. And we are basically focused on designing of antennas that create or that support a non-confined modes, not confined modes. Confined modes में क्या होता है, रेडिएशन लॉसेस बहुत कम होते हैं. ठीक है, क्योंकि मोस्ट ऑफ द वेव क्या होता है, बाउंस बैक होने लगता है स्टैंडिंग वेव्स में, क्योंकि उसकी बाउंड्री कंडीशन परफेक्ट. मेटेलिक बाउंड्री कंडीशन एक्चुअली जब आप मेटल बाउंड्री कंडीशंस की बात करते हैं तो वहाँ दैट इज परफेक्ट बाउंड्री कंडीशन, मेटल एयर बाउंड्री कंडीशन आर परफेक्ट बिकॉज टेंजेंशियल कंपोनेंट इज इक्वल्स टू 0. ओके, सो जितने वेव स्ट्राइक करेगा वो क्या हो जाएगा वापस, ठीक है. while in case of dielectric air bound condition is not perfect because E tangential is not equals to 0, ठीक है. अगर वहां पे लॉसेस होंगे तो क्या करेंगे, वेव क्रॉस कर देगी उसको. ओके, तो ये है. नेक्स्ट इज millimeter wave MIMO dielectric resonator antenna. Millimeter actually, if I am talking about the millimeter wave, there is one more advantage. Actually, the size of DRA, if you see the size of DRA is larger as compared to the printed antenna because this is a 3D structure. Okay, and its size is directly proportional to lambda over under root epsilon r. Okay, as the value of lambda is reducing, then size is also reducing. Okay, so when we are talking about the millimeter wave where the frequency range is more than 40 gigahertz, okay, then in that case skin effects are more severe. Okay, at the same time the size of DRA is lesser. तो यहाँ पर दो एडवांटेज मिल रहे हैं हमको. एक तो जो प्रिंटेड एंटीना का ड्रॉबैक था कि स्किन इफेक्ट वहाँ पे सीवियर होता जा रहा था जैसे जैसे फ्रीक्वेंसी बढ़ रही थी, तो यहाँ पर वो चीज़ नहीं है बिकॉज वी आर यूजिंग डाइलेक्ट्रिक मटेरियल एज अ रेडिएटर. ओके, अनदर थिंग इज दैट इसका साइज भी कम होता जा रहा है बिकॉज हेयर द साइज इज डायरेक्टली प्रोपोर्शनल टू लैम्डा. एज द लैम्डा इज रिड्यूसिंग, size is also reducing. Okay, so that's why when here the authors have designed the antenna at 28 gigahertz, so size is 9.5 into 7.5, 2.54 mm, and if you see the gain value which is approximately equals to 10 dBi. Okay, it is not possible to achieve such a gain on that frequency with the help of printed antennas. This is the advantage of dielectric resonator antenna. This is the another phenomena which is a filtering. I have already discussed this thing initially, that right now we have right now actually if you see the front end of the communication system, there is an antenna and after that we are using the band pass filter. So right now antenna engineers are focused on designing the antenna that itself behaves like a band pass filtering structure. Okay, so by creating the radiation null, so here the authors have used two different stubs to create a radiation null at 1.56 gigahertz and 2.25 gigahertz, and due to these radiation nulls, if you see the gain value is less than minus 30 dB. Gain value is minus 30 dB. Okay, 30 dBi just outside the operating band. Within the operating band it is approximately 5 dBi, while just outside the band it is it is less than minus 30. Okay, so if the gain is less than minus 30 just outside the operating band, then it is not, the antenna is not capable of receiving the radio waves. Okay, because gain is very less. Gain is basically tells us about the receiving capability of the antenna. Okay, the gain is less than there is no possibility of receiving the radio waves. Okay. Another one is a quasi-isotropic antenna. Quasi-isotropic antenna is basically actually isotropic radiation pattern is hypothetical in nature. It is we cannot achieve such type of radiation pattern that having the equal radiation in 3D space. Okay. Right now some of the authors have developed this phenomena where they combine the magnetic dipole and electrical dipole on a same frequency and create a radiation pattern which is omnidirectional in nature in both the planes, that is E plane and H plane. Such type of antenna that having omnidirectional radiation plane in E plane and H plane, दोनों planes में क्या है omnidirectional radiation pattern, such type of radiation pattern is known as a quasi isotropic radiation pattern. Okay. So here the authors have developed some uses some aperture or slot that behaves like a magnetic dipole, and also excite the DRA with the help of this strip which behaves like an electrical dipole, and combine both the dipole on this frequency and create the omnidirectional type of radiation pattern. 2 or 3 papers are available on this topic. Okay, quasi isotropic radiation, but it is very important because when you are talking about the antenna design for IoT, where we have a large number of wireless sensor nodes, then you have to use such type of radiation pattern, okay, that having the that is omnidirectional in both the planes. Thank you.
Any question from audience? Okay, thank you, Dr. Anand Sharma, sir, for being the part of this 1 week ATAL FDP titled Unlocking the Future, Exploring the Transformative Power of 5G and Beyond, and powering your knowledge with us. Your guidance is certainly going to groom the academic and research career of young faculty members, researchers, and industry persons. Once again, on behalf of Electronics Engineering Department, Rajki Engineering College, Sonbhadra, and our whole team of ATAL FDP, we are grateful to you for accepting our invitation and delivering a talk in 1 week FDP. At the end, I would like to request I would like to facilitate Dr. Anand Sharma by presenting a token of love. Okay, Professor Sharma, nice presentation.